Good morning, everyone. Am I audible?
Yes, sir.
Okay, thank you. So in today's class, I will talk about uh, the effect of leakage inductance in the line. So uh, we'll talk about effect of leakage inductance in the source side. Basically line inductance. It is not a desirable inductance, but leakage inductance exists. Let us say that LC uh, in uh, the commutation commutation of currents, right? Effect of leakage inductance in the source side, that is the line side, and it is LC. Leakage means it is not a desirable inductance. In the commutation of commutation of currents of thyristor, as well as the line side current. So let us draw it first. Let us draw the bridge first. Assume that the current is the load is again a constant current source ID, and its voltage is VD. Voltage across this is VD, right? And this is the thyristors 1, 3, 5, 4, 6, and 2, and these are the supplies. And now we are putting an inductance in the source side. This is the supply, basic supply. Let us call it VAN, and this is LC. This current is IA, right? Similarly, let us define other phases as well. So this is minus, plus, sinusoidal source, N. This is the N neutral point, right? Right, and then these are the uh, leakage inductances in the, this is the leakage inductance in the B phase, and similarly I draw the leakage inductance in the C phase, minus, plus. So we want to study, these are the thyristors, so let's put these gate terminals, right? And then this is this thing, this current is IC, this current is IB, right? This is the system we will be studying. So first let us draw our conventional three phase, 1, 2, 3, 4, 5, and 6, and then this is VAN, and this is VBN, and this is VCN. So VAN, VBN, VN, and this is VCN, right? And you know that this would be the 0 degree for the firing angle. This is the 0 degree after 30 degree. After 30 degree, 0 degree is the firing angle, reference for the firing angle alpha. That means 30 degree is the is corresponds to alpha is equal to 0, and then you do a firing at some point. I am arbitrarily doing, but for sake of convenience of drawing it, I am doing it at as if alpha is equal to 30 degree. It could be anything, okay? So I am just doing it so that we can quickly draw things. So I will draw this part. This is when TH1 is conducting. So let's draw essentially. So first let us draw if there are no leakage inductance, that will be the current. Current will rise sharply. You see, this rise will be sharp and fall will be sharp. Because there is no leakage inductance, nobody is stopping the current to rise in an instantaneous manner, in a discontinuous manner. Nobody will be able to stop if there is no leakage inductance. So let us first draw that way and then consider what is going to happen when we consider the leakage inductance. So this is this, and let me bring it sideways a little bit. Okay. So this is this, and when is VB is trying to conduct? VB is trying to conduct in this zone. IB is trying to conduct in this zone. That means this is thyristor 1 and this is thyristor 3, and I can complete the drawing. I can complete the drawing here itself, and I can complete the drawing of this. Right. Interesting point is what we look at it is this instant. What is happening? This is steep. This is discontinuous or steeply rising and falling currents. We'll see if LC is equal to 0. This rise and fall of currents are sharp or instantaneous. That is sharp or instantaneous. But when there is a leakage inductance, what will happen is the current will not be allowed to do in a very quick manner. So it will have a finite time before it comes down to 0. This will be taking some time, right? At least, and in the beginning you understand it qualitatively, right? And here the current cannot rise fast, and total current being same. So this current, this will rise in a slow manner, in an increasing slope. The slopes will be such that finally let us say this is IA and this is IB. We are considering commutation here. This is the instant we are considering. This is commutating instant, where what you have done, actually what you have done is you have given a firing pulse here. Thyristor, this is thyristor 3 has got a firing pulse here, right? The thyristor 3 firing pulse here, if there were no leakage inductance, the current would have in thyristor 1 would have changed sharply and would have come down to 0 instantaneously. However, this is not happening because there is a leakage inductance. It won't let the current to fall instantaneously to 0. So what will happen is it will fall with a slope. We will decide what is the slope. It depends upon the applied voltage at that instant in the circuit that we will calculate. But qualitatively, you can easily understand the current will take some time. And similarly, this current initially was 0. And since there is a series inductance in the line, so this current will take some finite time to go up. But while doing this, since it has to follow the Kirchhoff's law, what will happen is that means what you are understanding is both this duration, let us say this duration, let us first indicate by an angle alpha and an angle mu, right? Where is alpha? Alpha is here. Where is alpha? Alpha is here. And what is this angle? This angle is 30 degree. And where the commutation is happening? Commutation is happening at this instant, which is nothing but from alpha 120 degree, right? You understood that. This is first is 30 degree, then firing angle alpha, and from the firing angle alpha, there is 120 degree conduction of the TH1 thyristor, and at that instant, TH3 thyristor gate has been fired. So what is happening then? A small duration. It is a small duration because the leakage inductance is not supposed to be having a very high value. So during that instant, both TH1 and TH3 will be conducting. There is no reason TH3 will not, once you give a firing pulse, TH3 will not conduct because the voltage across it is positive and you have given a gate pulse, so it will start conducting. What the difference will be there is that current will not build in it instantaneously, and the current will not decrease in thyristor 1 instantaneously. So for some time, both the thyristors are on. So this duration mu, for this is for mu, which is called commutating interval. Which is called commutator. Both TH1, both 1 and 3 are on. I am just taking this as an example. So every transition, such kind of things will be happening. But we are now focusing our attention on this instant and trying to go into details and see what is happening. What will be the slope, and what will be the voltage drop, and what will be the at that time rectified voltage VD. So all those issues will be now determining. But understand that this kind of transitions are there. How many such transitions are there? There will be 6 such transitions, right? Both at the positive edge and at the negative edge of the current. Both when the thyristor 1 current is increasing as well as when it is decreasing. Because when thyristor 1 current is increasing, thyristor 5 current is decreasing. From thyristor 5, thyristor 1 conducts, and from thyristor 1, thyristor 3 conducts. So see, such situations are, it is like a relay, 1, 3, 5, 1, 3, 5, this kind of sequence the top thyristors are conducting, and similarly the bottom thyristors are also conducting in such a sequence. So there will be 6 such transitions, but at the moment we are concentrating on the instant when thyristor 1 is turning off and thyristor 3 is turning on. Okay, so let's do some kind of analysis here. So I will be doing an analysis taking let me write it in the bottom a little, but I need another page soon. So let's why is that gone? Okay, let me take a fresh page then. Okay. So lifting up is gone. Okay, might be gone. Okay, so let us now do the analysis. You can see that VAN, I can write VAN. Tell me what I can write as VAN. So you see the previous page. What is VAN? VAN is VAN. A little bit, this part has gone. So VAN is equal to L dia by dt plus VD dash. So what is VD dash? VD dash is why this bottom thing has gone? I cannot shift it. I cannot. Okay. So what I do is okay. Page 1. Okay. So okay, what I do is that I write the equation a little bit, or I will one more time I will draw it. LC dia by dt plus V d dash VD n. Achha, what is the equation? Let us see one of them. You probably will understand it. This is the equation. This is TH1 is conducting. This is minus plus. This is VA. This is LC. This is IA. So this is going, this thyristor is conducting, 1 is conducting, and it is connected to this point. This point voltage is V D, right? VD with respect to let me call it VD dash, VD dash with respect to this neutral. So this voltage I am calling it as VD dash N. So you see the Kirchhoff's law, with respect to N, this is VAN, then this drop L di by dt, LC dia by dt, that is the second part, and then you get this voltage. So this is coming, and then VD dash into N. This is the DC positive terminal. So DC positive terminal voltage is VD dash with respect to the neutral point voltage N, right? I am not talking about VD is between positive and negative terminal voltage. This is VD. This is VD voltage. So this is the for the A phase, that is the equation. VBN similarly, that is also conducting. So another phase that is conducting is, you see what is conducting is this phase, and TH3 is on. This is 3 thyristor is on, right? So I will write it as VBN is equal to LC dIB by dt plus VD dash N, right? So another equation is these two things together by Kirchhoff's law must be equal to ID. ID is the current here. ID is the current here. ID is the current here between the DC bus. So I know IA plus IB is equal to ID. So DIA by dt is equal to minus DIB by dt, because ID is a constant. ID is a constant. This is a constant. So this is true. So VAN is equal to LDIA by dt plus VBN minus LDIB by dt, which is equal to L is LC, sorry, LC, right? Always LC, which is equal to 2 okay. So what is okay? Let us cancel it. What is VAB? That is VAN minus VBN. That is equal to 2 LC DIA by dt, right? So now I can find out what is VD dash N. What is VD dash N? It is nothing but VAN minus LC DIA by dt, which is nothing but VAN minus LC, and DIA by dt is VAB by 2 LC. So this cancels. So which is nothing but VAN plus VBN by 2. Correct? This is VAN plus VBN by 2, right? So I know I have reduced the number of variables quite a bit, and I have found out this one, right? So now I have to do what is I. Now I will find out what is I. This is the equation I will use and try to find out what is I. Now quickly draw. Let us see what is the VAB. As far as the phasor diagram is concerned, this is ABC sequence. So this is VA phasor, this is VB phasor, and this is VC phasor. So VA minus VB is leading by 30 degree. This is VAB, right? So if I consider VA is equal to, I am writing in terms of line to line, √2 V line to line voltage by √3, that is the phase voltage, sine of omega t. If that is the expression of VA, then you agree that VAB will have the expression of √2 VLL sine of omega t plus 30 degree, right? So I know the expression of VAB here. I know, and I need to know what is the value of current here. This is a very clean expression. Only thing is the leakage inductance of the line is to be known. Let us say we know this by some means, by some by some what to say experiment. We have pre-calculated this value LC, and we now need to know the expression of the current IA. So we will do this in the next page. Right. So we are doing the calculation of it. The equation is dIA by dt is equal to VAB by 2 LC, and VAB is equal to root 2 V line to line sine of omega t plus 30 degree by 2 LC. So IA is equal to root 2 VLL by 2 omega LC into minus cos of omega t plus 30 degree, right, plus an integrating constant. This A is the integrating constant, is a constant, integrating constant, just to match our initial condition. So what is the initial condition? Initial condition is IA at a t, IA is equal to ID at omega t is equal to what? Omega t is equal to first 30 degree plus alpha plus 120 degree. So it is 30 degree plus alpha plus 120. That is the commutating instant. That is the constant. 30 degree is the initial. Then your own definition of alpha, and then 120 degree is the conduction. So at the end of A phase conduction, that is end of thyristor 1 conduction, the commutation instant is happening. So we are analyzing that commutation instant. So this angle is corresponds to 150 degree plus alpha. So let us put that ID is equal to root 2 VLL by 2 omega LC into minus cos of 180 degree plus alpha is equal to plus A. So what we get is A, integrating constant A, is corresponding to so we can find out the A is equal to ID minus root 2 VLL by 2 omega LC into cos of alpha. Right. So this is what is the integrating constant. This. Then we'll find out actual value of IA. So IA is equal to, again we put the value of integrating constant there, root 2 VLL by 2 omega LC minus cos of omega t plus 30 degree plus A. A is equal to ID minus root 2 VLL by 2 omega LC into cos alpha. So we know what? We know that at the end of the commutation, IA current has become 0, right? This is IAT. So at the end of commutation is when? At the end of commutation is when another mu angle has passed. You remember that commutation is happening this way, right? This is where commutation is happening. This is the current IB. This is the current IA. It is changing from ID to 0, and this is changing from 0 to ID. And this duration, this overlap, this is called overlap duration, is called mu. Mu is the overlap duration. So we know that. So what is the angle taken from this? So that is that we know that at omega t is equal to when? First is 30 degree, then is alpha, then is 120 degree, then is mu. At that instant, at ID, IA must be equal to 0 because commutation has ended. It cannot take negative current. Thyristor cannot take negative current. So at that point, the thyristor current has become thyristor 1 current has IA is also correspond to, I can say that ITH1 current, and IB is corresponding to ITH3 current, right? So this current has become 0. So by putting this condition, 0 is equal to this, 0 is equal to what we will put is root 2 VLL by 2 omega LC into minus cos of alpha plus 180 degree plus mu minus cos alpha plus id. This will put, after putting that, we get a thing like we get this situation. This implies that cos alpha minus cos of alpha plus mu is equal to id to omega LC by root 2 VLL. So this is the thing, expression. This is a very important expression that we are getting. Right. So once I have got that, I will progress further and calculate what will be the mu. So we want to know how much time it will take for this thyristor to commutate, to come from ID to 0 and from 0 to ID. ID to 0 for IA current and 0 to ID current for IB, 0 to ID for IB current. So we want to know how much is that duration. Though duration implies time, I am just talking in angle. You can easily convert them into time. Omega t is equal to mu. So mu divided by omega will be the time. So let's take another page, and we can write that from the previous expression. We can write that mu is equal to cos inverse cos alpha minus 2 omega LC ID by root 2 VLL. VLL is the line to line voltage, okay, minus alpha. So this is this. So you know what is the duration? This is the overlap duration. Overlap duration. So what are the consequences of overlap duration? What is the consequence? First of all, before going there, since you have found out IA current, you can easily find out what is IB current, because IB is nothing but ID minus IA. So once you know the expression of IA, which we have known, we can easily find out the expression of IB. So let us say the second part. See the second part. The second part is that what is happening to the DC voltage, the rectified voltage that has been produced. We know what otherwise would have been produced is what? We know the formula that VD is between plus terminal and negative terminal voltage. That is 1.35 into VLL, line to line, into cos alpha. That would have been the voltage. Now you see, due to commutation, you can easily understand that this voltage will reduce, because some of the voltage is spent on the purpose of commutating the currents of the phases of the thyristors. That is spent there. So the voltage that otherwise would have come to the rectifier side is now little bit consumed. Some part of it is consumed in the thyristor, in the commutating inductor to change the slope of the current, right? So let's see how much we have lost. How much we have lost is, you think that, you see the let us see the pages. No, previous. Yeah, you see that in this figure, if there is instantaneous commutation, that means current changes from TH1 to TH3 instantaneously, then what happens? The point potential VD dash is that point potential becomes how much? VB. That point voltage becomes VB, because this is minus plus VBN. Instantaneously the voltage becomes VB. That we are not getting some other voltage, right? How much voltage you have got? We have understood that VD dash, we have written that it is VA plus VB by 2. Instead of getting VB, let me write it in another color. Instead of getting VB, we are getting VA plus VB by 2, right? VB is for no commutation. Then the voltage will be VB. This voltage will directly come to, because TH3 is on, because the green case is TH3 is on, so it will be VB. But instead of that, we have calculated that we will get VAB is equal to, here we have calculated here that it is equal to VAN plus VBN by 2, right? VAN, let me write it more clearly, VAN VBN by 2. Now go to the right. Now, so therefore the loss, how much voltage we are losing? We are losing volt second. Let us say voltage second. How much voltage you are losing? VB would have been VBN minus VAN plus VBN by 2. Okay, so this is equal to okay, into voltage into second. And how much time it is happening? It is happening for the duration from as far as this is concerned, I'm writing in terms of angle is 150 degree plus alpha to 150 degree plus alpha plus mu. If you want to be very correct, this is divided by omega, right? So this is the volt second. Losing volt second is this. It should have been VBN. Instead of that, we are getting VAN minus VBN by 2, which is nothing but we have to integrate 150 degree plus alpha by omega by, or let us say not write omega, let us change it to 150 degree plus alpha plus mu into this is equal to VBN minus VAN by 2, right? VBN minus VAN by 2 d omega t by omega, right? So this integration, if I do, I will get what is the volt second of this, right? So what is VB minus VA? VB minus VA is what? Right? This is V. This is VA. This is VB. So this is sorry, VB minus VA. So this is minus VA. So this is minus. So this is about at an angle 150 degree. This is VB minus VA is at an angle of 150 degree. So you put that and integrate. So this is equal to integration of 150 degree plus alpha to 150 degree plus alpha plus mu into half omega root 2 VLL into sine of this what? Omega t minus 150 degree and d omega t or d theta. So this is the integration if you do, and if you continue to do this integration, you will see that the amount that we get is half root 2 VLL by omega into cos of mu plus alpha minus cos alpha. The expression that we had earlier found out, right? So this is the expression. This is the amount of loss in volt second, losing volt second. That is the volt second we have lost due to the commutation of the thyristor. The expression is half into root 2 into VLL by omega into cos mu plus alpha minus cos alpha, right? So, okay. So this volt second you are getting, and okay. So this is the volt second you are losing, and for one commutation, okay. So first find out what is the average loss. Average loss. First find out for 6 commutations, because that is happening in a commutations. The loss in volt second is into 6. So it is equal to, corresponds to 6 by 2 root 2 VLL by omega cos of mu plus alpha minus cos of alpha, right? Cos of alpha. So this is the loss in volt second, cos mu plus alpha minus cos alpha. Okay, so now let us find out what is the average of it. Let's add one page. That means what is the average of it, right? Average of it means divided by 2 pi. So it will be 6 by 2 root 2 VLL by 2 pi into, this is 2 pi. This is what is done by averaging over the period. So that is into cos of mu plus alpha minus cos alpha, right? So if you replace this, already we have got an expression for this. If you replace it, where is the expression? Let's go back to this page. No, previous. What is the expression of this? Here you see cos alpha minus this is equal to this, that is equal to id 2 omega LC by root 2 VLL. So that means that is equal to id 2 omega LC by root 2 VLL. id 2 omega LC by root 2 VLL. I have to remember that id 2 omega C by root 2 VLL. Next is equal to 6 by 2 id 2 omega C by root 2 VLL, right? And this is negative, right? This is a negative. So this is equal to the loss is equal to minus, if you check cancels this root 2 and 2 and right, and this is 3 and omega, if I replace as 2 pi FC, then pi also cancels. So it is equal to 6 id f into LC. This is the amount of volt second that is lost. So therefore VD is equal to, it should have been 1.35 VLL cos alpha. Instead of it is getting this minus 6 id f into LC. It doesn't depend upon the system voltage. Look at this. This doesn't depend upon the system voltage. It only depends upon the current ID and the frequency and the corresponding. It is, you are seeing that it is getting some kind of omega L drop. You can see that it is getting some kind of omega LC into F into ID. This is some kind of omega and then ID, but there is a coefficient 6. So this much will be the loss in the rectified output voltage. This is the rectified output voltage with commutating inductance considered. With commutating line inductance considered, VD is the voltage, rectified voltage. This is the rectified voltage with the leakage inductance in the line, right? So this is what we understand, and therefore if we go back to our first rectified waveform, Let's try to go back there. No. Yes. So we had seen the rectified voltage would have been what? Would have been this kind of uh, uh, thing. Let me try to sketch it one more time. Let me try to sketch it here. So 1, 2, 3, 4, 5, 6. So you see rectified voltage I want to sketch. This is this and this is this. Okay, this is this, right? And right. So you know that the voltage is under rectified condition is how much we said that is equal to VAB. Let me go back. It is V this. Okay, so VAN plus VBN by 2, right? Right. VAN plus VBN by 2. Okay. Okay, that is the voltage here, rectified voltage VAN plus VBN by 2, right? VAN plus VBN by 2, right? So here, okay, so you see that instead of getting a voltage of VB, we are getting a voltage of VAN plus VBN by 2. So let us see what is VAN plus VBN. So let's go back to the page. Right. So this is so VBN, VA is here, VB is there, VAN plus VBN is here, right? And divided by 2, right? So instead of getting a voltage of VB, which was this, VB magnitude is this, we would be getting a voltage corresponding to this calculated at the instant. So VAN plus VBN by 2, what is the expression? That is equal to, say magnitude wise it is the same, that is root 2 VLL by root 3 into another 2 is division is coming here, sine of omega t minus 60 degree. That is the expression of VAN plus VBN. Whereas VBN is equal to what? Root 2 VLL by root 3 into sine of omega t sine of omega t minus 120 degree. Okay, let's say that instant of this thing is this is corresponding to omega t is equal to how much? Omega t is equal to, let us say alpha is equal to 30. I'm just giving an example, 30 plus 30 plus 120 degree. Let us say in this instant. In this instant is how much? It is equal to 1 omega t is equal to 180 degree, right? Right. So at 180 degree, So VBN is equal to root 2 VL by root 3 into sine of 60 degree, right? This is the magnitude of the voltage. It should happen when the rectification is happening. Rectification is happening as per our thing is this instant is rectification is happening. This is the instant we are talking about. This is the instant when the rectification is happening at that instant. So at this instant, the output voltage should be of this value. That means root 3 by 2. So it is root 2 by root 3 into VLL into root 3 by 2. So this cancels. Its magnitude is VLL by root 2. So that is the magnitude of the voltage that should be rectified voltage as an output. Whereas in this case, what is the voltage? This voltage will be root 2 by root 3 VLL by 2 into sine of 180 minus 60, that is equal to 120 degree. So 120 degree is also having the same value as this, but the value is half now. So here also the value is the same. Root 2 by root 3 VLL by 2 into root 3 by 2. So you see it has the same value, exactly same value, but half. So you are getting half value here. So rectified voltage would look like, you know, would look like, let me say in this instant, whatever the rectified voltage would have happened in this is VD. Whatever the voltage would have happened, it will not be this. It will be half of that value will be coming here. So there will be a glitch. There will be a sudden drop, and this is called the commutation notch here. In this case, there's a commutation notch is called. In the rectified voltage, there is a sudden drop in this, and that will be called a commutation notch. The output voltage otherwise would have looked like what? Let me do it. Otherwise, okay. So let me do that. No, let me not do that now. So you can, but concept that this there is a drop in output voltage during the commutation. So that is the idea. And you have calculated in this case how much is the drop. Drop is half. In one case it is VLL by root 2, and another case it is VLL by 2 root 2. VLL divided by 2 root 2. This is the second one. This is the second one, VLL divided by 2 root 2. So this way there will be a dip in the voltage for a small duration for a timing time corresponds to the commutation angle mu. There will be a drop in the voltage. You can try to draw it. But before, since I want to touch upon a very small topic, I am not drawing it. I want to touch upon a small topic, which is that I am always saying that the firing angle is here, right? How do you fire? I have always said that 1, 2, 3, 4, 5, 6. What I have said is that right. What I said is first you give 30 degree, then your firing angle alpha is equal to 0 here, and then you try firing angle alpha anywhere. This is the alpha, let us say. That is what I have said. Now, how do you get it? How do you get it? So you know that earlier I had talked in the case of single phase like a modulation scheme that is called the cosine modulation. So let us say we want to develop a cosine modulation scheme for this. So if I want to, let us say we are now concentrating on thyristor 1, TH1, and for that I want to have a cosine modulator. So cosine modulator means we have to have a cosine function, and the cosine function 0 will be at 30 degree. This angle, this gap is 30 degree. So this gap is 30 degree. So this 30 degree, the cosine should have its peak value. So that way it would has to be constructed. So cosine waveform has to, we have to have a cosine waveform, which is this, which means that it is coming to 0 is this, coming to 0 is this, and then this is 60, 90, and this is 0, this is 0, 30, 30, and 60, 90, then 60, 30. Okay, here, yeah. So this, and then this. You understand, I hope. Exactly, I am repeating the same idea that we needed. This is for cosine modulator. For cosine modulator. What is the idea? If you compare with some reference, as reference, V reference, you see that it has cut here. It has cut here. So this would be corresponding alpha, and that alpha will be given by what is that? If I call it as a as V carrier, V carrier VC. So what is the idea? VC cos alpha is equal to V ref. That is what the job of a cosine modulator is. It should produce such an angle alpha, right, related to the reference voltage Vref. This Vref is related to the eventual output. This Vref is eventually related to the event output, so that Vref and the eventual output Vd are linearly related. These two things are linearly related. So the modulator's job is to produce such an angle alpha. That's why you require a cosine modulator, because this alpha in such a way that Vref is related to alpha by the expression Vc cos alpha, where and the output voltage, actual output voltage Vd is related to 1.33 VLL 1.35 VLL cos alpha. So this cos alpha, if I replace it by this VLL, if I replace it by this, then Vc is the carrier waveform, which is a constant, peak value of the carrier waveform, which is a constant by so then it is representing Vref by Vc. So there is a linear relationship between Vc, Vref, and Vd. That is the objective. It's fine. Now, can we get this? Now you see, this is an awkward waveform. Suddenly one cosine waveform we have to get. So can we get it? It so happens that there is a way we can get it. If we can get it, in which way you can get it? Let us see which way you can get it. We know that there is a, if this is A phase waveform, the B phase waveform is coming here, right? B phase is where? 1, 2, so B phase waveform is here, right? This is the B phase waveform. B phase waveform is here, right? Now see a beautiful relationship between B phase waveform and the modulator, cosine modulator waveform that we would intend to produce. What is the relationship? That if I just negate VB waveform, I get actually the cosine waveform. So what I cosine modulator waveform. So what I should do as a carrier waveform, VC is nothing but VB. Vc is equal to nothing but minus Vb, right? Negating the Vb, I will get it. Obviously, some scale you can produce. So some scaling is okay. Some scaling is acceptable because Vb is a line voltage. You will anyway directly not use it. It is a high voltage and power. You will scale it by a transformer trans ratio. The K is the trans ratio we can think of. You are producing by a trans ratio, but you take Vb waveform, and you convert it into the scaled Vb waveform. K Vb waveform, and which you use it as the modulator waveform Vc. Vc is essentially an expression of capital Vc cos alpha. Capital Vc is the magnitude, Vc is the carrier for TH1 firing. So you see, the basic point is that you don't need to do very complicated signal processing to get cosine waveform. Cosine waveform is in a three-phase system, is there in another phase. if you cleverly pick it up, you will get the cosine waveform. And in this case, the cosine waveform is nothing but minus VB, right? That is what we understand, that we need not do this. However, you may argue about one minor part. That minor part is that this waveform is what to say, has a period that is half, right? Because we are again and again repeating this waveform. After 180 degree, we are rectifying, and we are not continuing with the VB waveform or minus VB waveform. We are rectifying it and producing it. So how do we do it? We can do it a little cleverly again by ending this waveform with another waveform which is positive only during this phase. So which waveform is positive only during this phase? You can see that if I draw VAB waveform, which is a positive, VAB is which one? VAB is 30 degree lagging, VA minus VB. So VAB is here, 30 degree lagging, is 30 degree lagging. So VAB 0 is here. It may have a higher magnitude, but doesn't matter. So VAB 0 is here. VAB 0, because it is 30 degree lagging. This is 30 degree. This is VAB 30 degree lagging. So VAB is here, right? VAB is here. Yeah, somewhere. Yeah. So 1, 2, 3, half. Okay. So somewhere it is here, right? So you see that it is synchronized with the cosine waveforms, cosine waveform of the carrier, right? It is half. It is picking up half the period of minus VB waveform, and by indicating that only I can take only the positive value of the VAB. So our carrier VC, I am writing qualitatively, it is minus VB into K when VAB is positive. So this will be our carrier waveform. This is the VC for PH1. In a symmetrical manner, you can generate the carrier waveform for all the other things, right? For this is the carrier waveform of A. So I am just mentioning A. VCA means carrier waveform for phase A, or carrier waveform for the top device of the phase A, PH1, is minus VB. Pick up minus VB or minus VB into K if you take into consideration the transformers turns ratio when VAB is positive. Similarly, you can do for V carrier of B. What is it? You write it. V carrier of C. What is it? You write it. In a similar manner, you can continue to operate. Okay. I hope this is clear, that this cosine modulation idea is possible in a three-phase in a very simple manner. You don't need sophisticated processing. The basic waveforms itself will help you to generate the carrier waveform, the cosine carrier, cosine modulator carrier waveform. So I think I have come close to that. I will request you to go through this, and if there is any question, please write to me, please email me, and any doubt if you have on this, please email me. I'll be not taking any more classes. I'll be handing over the classes to Professor Dipankar Debnath from next Saturday. However, I want to remind you that your test on thyristor and diode converters will be conducted on 7th November. Please write the test, and hope that you will do well. And in between any doubt, please feel free to write to me. I'll be available. So thank you very much for your time, and best of luck.